Welcome. This is PHY 2049L. It's a laboratory class, and the laboratory we're going to look at today is the intensity of light lab. And it's a dry lab because for one reason or another we couldn't be in the lab together today. So this is a way of making up for a missed lab. And let me explain what's going on initially. So we're going to use this equipment. This is the optical bench. It's just to keep everything aligned. And then at one end of this we're going to put the light source, and it's just a 40 or 60 watt incandescent light bulb. We use frosted glass so that the detector would not be looking at some very bright localized places. It would look at a general area of brightness. And then down here we have, at the other end, we're going to put a detector. And so this is a photocell, basically a little light detecting chip, semiconductor. And it's connected to an amplifier, which then sends it through to our system. And the next piece of equipment we send it to is this it's a Vernier Lab Pro. It's basically a digitizer. It takes a signal and it makes it into a digital signal, which can then be sent through to a computer. And that's going to run a piece of software called Logger Pro. So this is interfacing. This is a way of digitally interfacing this system. So what we're going to do is we're going to adjust the position between the light source and the detector. And we're going to see how the intensity of light changes as we make that change. Compare it with the theory. So let's begin taking some notes. So we're going to say this is going to be lab. It's probably 10 or 12 or something. So just look up which lab it is. And this is called the intensity of light. And don't forget, you always put the date down, and for every page you write on or stick something on, you put the page number in the corner. And as always, you want to be concise. So if we look at our objective today we I'm just trying to think of the right word actually, because we're going to retest the theory of how intensity of light relates to source power and source detector distance, separation, I say, separation. So we're not specifically trying to find a constant of proportionality. We're actually, there's not a real constant proportionality we can look at. We're going to just check out this theory. It's a little bit vague in that respect. So let's do some theory. and this will become a bit clearer. So the next put down is our theory And the theory says that the intensity of light is equal to the power of the light source divided by 4 pi r squared. And you might ask, where does that come from? And if we say this is our light source, so this is our source, as the light photons leave the source, they spread out over bigger and bigger spheres. Let's draw this on a different scale. And if our detector is at a certain distance, then that means that from that light source, that light energy has spread out over a sphere that has an area equals 4 pi r squared. So what that means is that whatever intensity it had at the beginning, it's been diluted, reduced by being spread out over this larger and larger area. The analogy we often use is we say, take a ping pong ball, take a softball, take a basketball, and take a beach ball, and take a can of paint and paint that object, and there'll be quite a thickness of paint on it. And if I go to the next object, the thickness will not be as great because the same amount of paint has been spread out over a larger surface area. And if I use an even bigger object, the paint will be even thinner because the area is so much bigger. And if I get the largest object, then the paint is even thinner. So the thickness of the paint is like the intensity. The thickness falls off with the radius of the sphere that the detector sits on. Now, as a teacher, I can confuse you a bit by saying, okay, I'm going to give you the area of the detector. And the area of the detector is not the area that we're talking about here. We're talking about the area of the sphere that the detector sits on. So this is my theory. Now, if I think about it, I'm going to measure I. I'm going to change R. And everything else is going to be held constant. The power of the light bulb. I'm not going to switch from a 40 watt light bulb to a 60 watt light bulb. I'm just going to use either a 40 or a 60. It doesn't matter, but I'm going to use a light bulb and stick with it. 4's a constant and pi's a constant. So if I remember that that intensity is equal to power over 4 pi r squared, then I is equal to power over 4 pi times 1 over r squared. And if I plot I versus r, which seems the most natural thing to do, I will get I versus r. This is an inverse square relationship. And the problem with inverse square relationships, like an inverse relationship, like a inverse 1.5 relationship, they all look like curves. They all look kind of similar. It's very hard to tell from the data whether or not you're following the theory. If I want to see if something is following theory, it's best to bring it to a straight line. It's called linearization. And so I'm going to plot I. So I am going to plot I, but I'm not going to plot R. I'm going to plot 1 over R squared. Not R squared, that would be inverse, 1 over R squared. If I plot I versus 1 over R squared, that's like Y is equal to slope X plus B. No B should go through the origin and should be a straight line. And this slope should be equal to P over 4 pi. Now, at first glance, this is interesting because I say to myself, oh, well, look, if I can find P over 4 pi equals the slope, I can find P, and I compare the power of the object to the power of the light bulb. And I have a closed loop then. I can look for an answer and get an answer, and I like doing that. But there's a problem, and the problem is that the intensity measure is arbitrary. It's not measured in watts per square meter, which in SI units it would be. If power is in watts and R is in meters, then this would be in watts per square meter. But you're using a piece of solar cell, a piece of silicon wafer to measure this signal. And so there's a mismatch. I get the units are either lumen or lux. And they're kind of like, they're not easily related to SI units. So I can't make that closed loop. But what I can do is I can collect my data and I can look to see, is it a straight line and does it go through the origin? And we've got to be happy with that for the moment. From an educational point of view, from a lab skills point of view, this is an example of collecting data using graphical methods and recognizing that I can't just plot down the two parameters, the parameter I change and the parameter I measure. I got to go to a second step where I linearize the information. So it's a bit more sophisticated in terms of its data processing, if you like. And so I look for, is I versus 1 over R squared linear? And 2 is I versus 1 over R squared passing through origin. If that theory is right, then the answer to both of those questions should be yes. We'll see to what extent it's not right. Let's go to the setup. So we have an optical bench, and we're going to have, they have little stands, they're little plastic clips, and then we have a light source. So there's my source, and then here's my R, and then here's my detector. And that's also on a little stand, actually. It's on two little stands. Makes it a bit of a pain to move around, so we move the light source rather than the actual detector. And this comes out and it goes to a preamplifier. when you have a small signal, you don't want it just wandering across the lab in a bare piece of wire. So you'll use coaxial cable, that helps. But also, if you can, you'll use a preamplifier pretty early on. And then you come along and it goes to our Lab Pro. That's a digitizer that changes a DC signal that's analog into a digital signal. And then it goes along and comes into our computer. And this is going to run a program called, I think it's 2Gs. If you, as you know by now, my spelling, I struggle with spelling. I think it's 2Gs, Logger Pro. And we're going to change R, and we're going to measure the intensity of light. So this is going to give us I. And we'll plot graphs of it. Now, because this is on a computer, we could put this on a computer. Just a little anecdote was, I used to work at the local university, and I was in charge of the labs as part of my job. And this was back in, this was 20 or 30 years ago. And computers, we didn't have a lot of money for computers, so we had one lab that had computers, and everybody would get to have a go at the computers. And I remember stood outside. I didn't teach the labs, but I would organize them. And I remember I'd stand outside the lab sometimes, and I'd say to the students, "So how was lab today?" And they'd go, "Oh, fine." And then I'd say, "So what did you do?" And whenever it was a computer lab, they'd say, "We did computers." And they might have done one experiment or another experiment, or they rarely focused on the physics of the experiment. They focused on the technology. Now, at that time, it was relatively new technology, so maybe it was a bit unusual. But I sometimes feel that, especially when you're learning the physics, the more sophisticated the system, to some extent, the less you think about what you're doing. That's not to say I'm not against computers. I think they have a really good place, and I try to expose my students to the computers, but not all the time. So just be mindful of that. It's not about the technology. It's about the experiment. The technology is there to serve the experiment. So we're going to need to collect some data. Now we become lab partners. So we're going to need to collect some data. So we're going to have, as always, your name and number table. So this is data table 1. You might have a report that has 17 data tables in it, and you can't guarantee what page it's going to be on when it's printed out, so you can't name it by the page it's on. Sometimes they have the same information, just changing with, say, the month of the year, So it's useful to be able to say data table 7 or data table 9, and people can find it very easily. In all your communications, you're trying to make it as easy as possible. So data table 1, and I never used to put down trial, but again, with experience, when you get data that's interesting, and by and large, when you're doing new stuff, it is interesting. Stuff happens you don't expect. You want to talk about it, and typically you'll talk about it in a discussion page. And if you want to talk about a specific pair of data points, an X and a Y, it's nice to be able to say, look at trial 7. And again, it's just very clearly done. So I do put down trial numbers now. And then well, I suppose the first thing I'm going to do is I'm going to set a value of R. And I'm a big believer in you write down what you see. And if R is in centimeters, write it down in centimeters. Don't do that change in your head, because if you do that change in your head, you will end up sometimes moving the decimal place the wrong way. We all do it occasionally. And if that's the only thing written in your lab book, you can't for sure correct it. You can assume you did it wrong, but you can't for sure correct it. So write down what you see. And then, well, associated with that, we're going to have a I. And my I is going to be in lux. If you noticed, I just paused the recording for a while because I couldn't remember if it was in lumen or lux, but it's in lux. Again, write down what you see. I'm going to leave some gap because I'm going to use this to do some manipulation. Now, the next question is, how many data points do we need? And my answer is, you need as many as it takes. And in truth, you don't know how many it takes until you've gone through this analysis and plotted out the I versus 1 over R squared graph. Now, that involves knowing how to set up the graph before you take the data. Well, that's not really true. That involves knowing how to plot the graph, having taken one piece of data. So the first thing I'm going to do is I'm going to go to what I think is the most extreme case. Why do we do that? We'll go to the most extreme case and we will measure the biggest intensity for the smallest separation. And so looking at my data, I can see, let's have a look, the smallest separation was, yep, it looks like 25 centimeters. So this was trial 1 and it was 25 centimeters, and for that it was 138 lux. Now what I can do is, well, then I got to do the next bits. I want to plot I versus 1 over R squared. So I'm not going to change lux, but I'm going to change R into meters. So go R in meters. And then go 1 over R squared, and that would be in meters to the minus 2. 1 over meters squared. And for that, well, we can do the first bit, can't we? 0.25. Move the decimal point that way. And then, sorry, I gotta move things around here. So let's have a look. Let's both do this. So it's going to be 1 over 0.25 squared. Yeah, 1 over 0.25 squared is 16. 1 over 4 times 1 over a quarter is 4, and then 4 fours are 16. So that's 16. So then, what I can do, this is the better way of doing it, is I get my graph paper. I'm going to go to the next page. I'm going to do this by hand, and you're going to do it on a piece of graph paper, and then I'm going to go and do it on a piece of graph paper in a bit. But remember, we always go about 3 steps up, and we go about 3 steps in. And we start off with 0, 0 in the bottom corner. You can't tell if a piece of data goes through the origin unless the origin is on the page. And then you turn around and you say, I'm going to have I vertically. Now you could have your page sideways or vertical, whichever you like. And then this is going to be 1 over R squared horizontally. And I, we said, was in lux. And then 1 over R squared is in meters to the minus 2. And then I look at my data. And I know that I need to have 138 is my lux measurement. Now, I'm hoping it's not going to fluctuate, but my decision is I'm never going to go closer than 25 centimeters, so I'm not going to get a bigger value. Why not go closer? The reason is that if I get too close, I'll start changing how much of the light that I see in my detector, because it's a diffuse detector, and I'm not sure if that's going to have an effect. So I'm going to keep somewhat distant. It's in these things, it's you want a variation, but you don't want to get too close to some things because you run into problems. Maybe my detector will saturate out and I'll get a maximum reading no matter what, because it's gone to its maximum range. So I'm being a bit conservative. So this is going to be 138, and so I start counting. You know, we know how to do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. Man, 14's not halfway up the page. So I go to 2 steps for each, and you know, etc. So I get a good scale. I want 1 to 2, I want 1 to 1, or 1 to 2, or never 1 to 3. 1 to 4 is okay, 1 to 5 is fine. 1 to 6, never. 1 to 7, never. 1 to 8, okay. 1 to 9, never. Because I got to do math on this thing. It's not a picture, it's a calculation. Got to do math on this thing. I don't want to have a wacky scale. So I'm going to go through, and I'm going to go, it's said 138, I'm going to call it 150, which is like 15. So I'm going to go, I'm going to do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's not bad. Actually, I just thought I could actually photograph a piece of graph paper, and then I can do this with real graph paper. So you're going to make a scale which is simple, where 138 is over halfway up the page. That's all you need, over halfway up the page. And we said that this was 10. I'm going to go 20, 40, 60, 80, 100, but that one a little bit longer. 120, 140, 160. There's no law says I've got to put every number in, so don't worry about that. And then for the 1 over R squared, this is the shortest value for distance, and so it's going to be the biggest value for 1 over R squared, and that comes out to be 16. So again, you count your way along and you use 1 to 1 or 1 to 2 or never 1 to 3. 1 to 4 is okay, 1 to 5 is better, never 1 to 6, never 1 to 7, 1 to 8 is okay, never 1 to 9, 1 to 10 is okay. And I come across and I work out my scale, and I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And this is going to be 1, 2, 3, 4. Let's do this in twos. 2, 4, 6, 8, 10, 12, 14, 16, 18. A computer could do this, but the problem is the computer would do what it wants. I really like you to do your own graphs. And then when you work with the computer, you'll be demanding of the system because you'll know what you want. So if I look at my first data point, then I have 16. So I take a line up there, and 138. There's 130, so 138 is like there. And then, of course, when I put my point in, I do a placeholder like that. Now, you don't have to have these lines. I like them for when I'm doing it freehand, but you don't have to have them if you're using a ruler. So then I got some other data. So I'm going to go kind of backwards and forwards because I want you to see how this works. So lab partner, let's go back and let's take our next data set. It's good to jump around. So didn't think about this last time. So we didn't jump around, but it's good to jump around. These are actually going to be in order, which is a bit of a pity, because if you get a systematic error which causes a problem, 1 or 4, I'm going to do them in groups. If you get a systematic error where the answer is just getting bigger because some amplifier is ramping up as you take the experiment as time passes, you won't notice it. But if you're jumping around, you'll notice those changes more. So that's 40, and then this is 72. And then if we go to the next one, which is 4, and this is 50, and then this is going to be 51. And then 100. Oh no, sorry. I'm rushing. Whenever you rush, you make mistakes. So this is 5, and this is going to be 100, and that's 20. And let's do those and see how they look. And so we come along and we say this is 0.32, and this is 0.40, and this is 0.50, and then this is 1.00. And then we look at this and we say 1 divided by parentheses 0.32 squared, and that's going to be 9.77. And then I go 1 divided by parentheses 0.4 squared, and that's going to be 6.25. And then we're going to turn around and say 1 divided by 0.5 squared, and that's going to be 4.00, and then 1 divided by 1 squared is 1. So there's my numbers. Let's go back to our graph and just see how we're doing. So we come along and we go, the next one it's 104. Let's do it the other way around. It's 977, which is 977 is just shy of 10. And then we add 104. And then I had 625. There's 6, there's 7, 625 is there. And then I had 72. 72 is there. Oops. And then we had 4 goes with 51. And then we're going to have 1 goes with 20. Okay, so again, let me just take these guys out. And I don't know if you can see it, but that's a little bit disconcerting because it doesn't look very straight. So let's get some more data. That's the advantage of plotting now. I'm much better informed about what I need to do to complete the lab, or at least get some more information. It takes us a little bit longer, but not much. So then let's do a couple more. So we're going to do 6 is going to be 90, and that is in 22. And then let's do 8. 7 is going to be 80, and that's going to be 26. And then 8 is going to be 70, and that's going to be 31. And then 9 is going to be, jump to the other end, 35, and that's going to be 89. And let's do those. So this is going to be 0.90, 0.80, 0.70, and 0.35. And then this is going to be, let's see if I can do this, it's going to be 1 divided by parentheses 0.9 squared, squared, not that, squared. And that's going to be 1.23. 1 divided by parentheses 0.8 squared is going to be 1.56. 1 divided by parentheses 0.7 squared is going to be 2.04. And then 1 divided by parentheses, and that's going to be, that doesn't make sense. Let's go back. 1 divided by parentheses 0.7 squared. Oh, it is. Yeah, okay. And then the last one is 1 divided by parentheses 0.35 squared. And that's going to be 8.16. So now I go back to my graph and I'm looking at these now. So I just did that 100. So I have, let's have a look. I have 1.23. So 1.23 versus 22. And then I get 1.56. 1.56. Can you see I'm clustering all these things down here? Not really helpful, is it? It's checking to see if it's repeatable. But I think I had the idea at the time that I was stepping nicely through R. And really, that's not what it's about. And then 2.04. 2.04. And that's going to be 31. And then 8.16. 8.16. Okay. 8.16, and this is going to be 89. So can you see how if you step evenly through R, 10, 20, 30, 40, 50, 60, 70, 80, because you're not plodding R, you're plodding 1 over R squared, you're not going to get a linear stepping through your graph. So that's something to be really mindful of, and this really helps you, because now I look at this graph and I go, you know, I want some things that are a little bit better. Unfortunately, when me and my lab partner did this before, we weren't thinking that through. And so these are real data taken by a group. So then let's have a look. We had 10. They went to 30. And they got 116. And then they went to 65. And they got, is that 116? Yeah. And then they got 34. And then they went to 85. And they got 24. So this is 11 and 12. And again, this is because they're not plotting the data. We didn't plot the data beforehand. We didn't plot the data as we were doing it. So you can't see the pattern until you've finished the experiment. So this is R becomes 0.30, R becomes 0.65, and R becomes 0.85. So then we say, okay, we're going to have, let's have a look, 1 divided by 0.3 squared, enter. That's going to be 11.11. 1 divided by 0.65 squared becomes back with 2.37, and 1 divided by 0.85 squared is 1.38. So then I come to my graph and we'll do our final bits. And if I look at my data, I have, let's have a look, 11.11 and 116. So 11.11 and 116 is about, 116 is about there. And then I have a couple of data points that aren't that useful to me actually. So 2.37, 2.37 is back down here, and that's going to be 34. Well, yeah. And then I have 1.38, 1.38, which is right in the midst. 1.38 is somewhere in there, and we have an answer of 0.85. I'm sorry, we have a value of 24. So yeah, somewhere in there. And let's clean this up. Didn't mean to do. I was a bit keen on that. Let's do that. Okay, issues. I'm going to stop and I'm going to go away and plot this out properly, and then we can see. But it seems to me I might be able to get a straight line through there, and then maybe another straight line through there. Or maybe I got a bit of a curve on it. It does kind of seem like there is a bit of a junction here. I would love to go back and take some more data out here and just try and distinguish, is this an elbow or is this just an arc? That would be really, really instructive. So let's stop. I'm going to go and plot this graph, and you plot the graph as well. You got to do the graph in your book, not freehand, but you know how to do it. You got to do it using ruler and graph paper. So, sorry, I got to get my pen out here. So this is what I drew, and hopefully you got something similar. You might not have drawn these lines on. First of all, I did the dotted lines to encompass the entire data set. And if I wanted to know the least slope and the greatest slope, I could use those. But that's including a data point that I'm really suspicious of. So first of all, I had a misplotting down here. I just crossed it out. This is a lab book. It's like, that's fine. It doesn't get in the way. But the second thing is that this data point up here is I don't know if I can spell it, anomalous point. It's an anomalous point. It doesn't follow the trend. There's this line which is reasonably linear, the red line, and then there's this guy way over here. So reasons for anomalous point. You can't just say, oh, I don't like it. You got to give, in your mind, you've got to have some resolution for it. And one is maybe amplifier is saturated. Maybe there's a maximum value and we reached it. Now, how would I know that? How could I prove that? I could do some more data points and see in that region there, do I always get the same value? If I always get the same value, oh, I know that, I'm saturated. Another thing that might be happening too close to the source. By using too close to diffuse source. By using a light with a frosted glass. If I am so close, I might only encompass part of the surface, and if I'm further away, I'll encompass all of the surface. And so I could be going from one mechanism, one mathematical mechanism to another as I get too close. 35 centimeters is still a long way away. I'm not convinced about that. If it was 10 centimeters, I'd be much more convinced. So if I had to guess, if you said, well, what's your best option? I would say, if you're going to do some more research on this, you need to do this stuff up here. That would be my first guess. Now, can you see how if we'd done this in the lab and cared about the results and because we're getting paid, it would have been easy as we're plotting the graph first of all, not to set so many data points down here. We don't need all that many data points down here. But secondly, to say, you know, we need a couple more data points up here just to see if we're saturated out. This corner, if it is a corner, is very interesting. And so there was more work to be done on this graph, but we didn't know because we collected all the data before we plotted the graph. And that's a rookie mistake. So try and get into the habit of, you know, yeah, you go to what you think is going to be a decent range and you get the most intense value and set up your graph. And then as you get data, start plotting it on the graph. This is a lab book. You can do that kind of thing. So I'm going to go to my conclusion. Number one, the graph seemed linear over a range of the data. There's an anomalous data point. 2, the graph, whoops, graph did not go through the origin. Let's have a look at that again. With my plotting, I'm a little bit out. I seem to have 10 looks no matter what. 3 background illumination. That's not spelled right, is it? Of 10 lux. Yeah, I had some background lights on in the room, and so they gave a light level which was independent on top of position of my light source. Maybe due to background illumination. It could also be due to an offset with problem with, say, my detector, but probably due to background information. Can you see how, in real terms, even a lab like this, if you really care about the results, if you're working for a company and you've got to convince a customer that the product is working well, there's often a lot to talk about. It's not just the answer's 27, I got 28, oh, that's close enough. There's a lot to talk about. And I found as a student that this aspect of my undergraduate degree, I found it fascinating. That's what science was for me. It wasn't doing the derivations. It was this stuff. I really, really enjoyed it. And for quite a few years worked in business using these skills to satisfy customer questions and the like. So in your junior year, sometimes the junior year is a bit of a slog because they're trying to get through all the hard stuff. But there'll be labs, there'll be projects. And if you approach the project with the right attitude, which is, man, can I get the right answer and get out of here? Or can I get the right answer and pass, which is what I started off with. But what's going on here? Then it can be fascinating. You'll enjoy it a lot more. So there's the lab. So write it up, and I'll see you guys next time. Okay. So don't forget, do your graph, do your data table, write it up, and I'll see you next time. Keep safe.